Hi again, Jim Brofel here from OLI Systems for another video on how to use OLI Flowsheet. So in this particular case, this is actually from my old past. We had a chemical plant that had a waste product of hypochlorous acid. This was actually in the production of chlorine, and a little bit of hypochlorous acid was left over from this process, and it was going to be piped back to the reservoir, which is about 10 to 15 miles away from the plant. The problem, the pipe was carbon steel, and hypochlorous acid will attack it and cause corrosion issues. So they wanted to control the amount of hypochlorous acid in that stream by using a reducing agent to turn something back into the hypochlorous acid back into chloride ions, which were, although not great for the pipe, were a lot safer than the hypochlorous acid. And what they used was sodium sulfite to do that. So I thought, let's do a simulation based upon my recollection of what was going on, and we'll take a look. So the first thing we did here is, since I know it's going to be oxidation reduction chemistry, is I went ahead and started some chemistry. Now, just as a disclaimer, I am using the mixed salt and electrolyte model, but this is valid for the aqueous model and MSc SRK as well. So my model contains hypochlorous acid, HClO, and sodium sulfite. So this is the reducing agent. It's going to reduce the +1 of the chloride of the chlorine to -1 of doing that. Now we know that's an oxidation and reduction chemistry, so I just went over to the redox tab and turned on those subsystems. Now, for the purpose of this tutorial, I'm not too worried about which subsystems are actually being used. In practice, I know that I don't have to worry about the +7s because they're not going to occur because I am reducing this, and I'm probably not going to get all the way down. I'm starting with a reduced form of sulfur. I don't have to really worry about the sulfides, the elemental sulfur, and so forth until I get up to the +4s and +6s. But for example, I'm just going to leave them all on. So I'm going to try to control the ORP, the oxidation reduction potential. That's actually what we used to measure the amount of sulfite we had to add. We wanted to add sulfite to reduce the hypochlorous acid, but we didn't want to add so much sulfite because eventually with time that excess sulfite will oxidize to sulfate and could potentially plug our well, because our well water also had calcium in it. So we could have formed gypsum or anhydrite in our well, which would cause other problems. So it was a titration, and we thought we could do it. So I went ahead and started this. My hypochloric acid stream contains 0.1 moles. This is rather an arbitrary amount at 25 degrees. My sulfite stream contains a corresponding amount of sulfite at 0.1 moles. I went ahead and ran it. Okay, this actually runs pretty quickly, so we'll go ahead and let it go. And you can see things go around. The target here is approximately 1 volt is what we're looking for here. And it's having some issues. It's getting there, but it's not happy. And after a ridiculous amount of iteration, we get to an error message that says, I can't converge due to a precision limit. That means my controller can't make a small enough step size to get within the delta around the tolerance around the controller set point. It just doesn't work. And I actually killed myself a little bit trying to figure out what is going wrong. And then I said, well, let's remember what's going on inside the model. So I want to take a look at the hypochlorite stream. I have a report here. I'll just go ahead and remove everything to make it easier to look at. And I want to look at just the hypochlorite. This is a stream summary of what's going on inside the hypochlorite stream. pH is pretty low. Well, it is an acid, so that makes sense. We're going to go down and look at all the properties. Everything here sort of makes sense until I get down to the species. And I look at the ClO ion, the hypochlorous ion, and it's essentially 0. These numbers are just here because thermodynamically they have to be there. But they're tiny. What turns out is that the hypochlorous acid stream has already reduced itself to chlorite. that makes absolutely no sense. But that is one of the problems when you have redox enabled, in that redox will give us the thermodynamically stable phase. And in this particular case, the chloride ion is the most stable form of chlorine in this calculation. So there's been no, it's already been reduced. Okay. If I go look at the sulfite stream, okay, we have an analogous problem that there's very little SO3. You can see here it's not as small, but it's still pretty tiny, and a lot of it has already converted to the sulfate form. So the redox has already taken place in the streams, these two streams, rather than in the mixer. Okay, and that could be a reason why I'm not getting the expected results in my calculation. So I will go ahead and save that, and I'll show you how I fixed it, or at least I think I fixed it. I created a new model. So let's go ahead and do that here. Okay, so I'm going to save this. I always save things when once something converges, I am going to save it. Model. I actually have a pre-saved case here. Do model 2, and I'll show you what I did. Okay, the first thing I'm going to do is I'm going to create a new chemistry model. We do it through chemistry and add a new chemistry model. Okay, and you see it added chemistry 2 up here. It has to be the same thermodynamic framework as the existing model. You can't have an aqueous model and an MSE model in the same flow sheet. That just doesn't work. The flow rates are the same. We actually copy these from the existing chemistry. So I still have HCl, I still have sodium sulfite. Okay. The only difference here is that I'm turning off redox. Okay. So these guys, let's go ahead and actually do that. Turn them off, turn off. So they're off. So there's no redox in this particular chemistry model. I'm actually going to rename this new model. You're allowed to do that with a rename command. I'm going to call it no redox. Now I go back to the flow sheet. I don't want redox calculations to occur in my feed streams. So I'm going to click here on hypochlorite. And over here in the chemistry model section, I now have another chemistry model to pick, and I'm going to pick no redox. I'm going to do the same for the sulfite stream and pick no redox. The mixer also has chemistry models, but I want redox to occur here, and that was in the original chemistry model, the default model. Okay, I think I'm ready to go, so let's go ahead and save it. I, again, always recommend you save. Okay, we'll go ahead and look at the output, and we'll hit the run button. This one may run a little longer because there are more calculations to do. I put an error band of 0.05 volts on my controller, and I got there. But the important thing to look at now is let's go back and look at those reports. Okay, this still here. If I look at the hypochlorite stream, I go back and look at the species, I still pretty much have all of my hypochlorous acid that I input. The only what happened here is it dissociated a bit, which is what we would expect for an acid. Similarly for the sulfite stream, everything here is still mostly the SO3 ion, the sulfite ion. So it hasn't reacted. There's a little bit of hydrolysis going on here to give us other forms of the S+4 material code, but no redox has occurred here. Okay. If I look at the final result stream, the mixed stream, we don't actually need to see the intermediate, you'll see that it's, in fact, has reacted all the hypochlorous acid. They're all tiny, and we pretty much end up with chloride and sulfate, wherever sulfate is here. There are other forms of sulfate based upon pH, a couple other complexes, and so forth. So that's how you can use a multiple model to affect your chemistry. In the background, there is actually a master model being built, so creating models is very quickly. You don't have to do a lot of typing. You may notice that the ORP values in my callouts are question marks. ORP is not a valid variable in the no redox case. So, it's oxidation reduction potential. Since there's no oxidation or reduction going on, those values, because they're in the callout, are question marks now, you can clean them up by editing the call out to get rid of them. If you don't like them. Okay, a much cleaner looking diagram. So that's how you use multiple models. Any questions, give us a call through the portal from OLI Systems, portal.olisystems.com, and we'll answer your questions. Thank you.